So let's take a look at a couple of proofs in this section. So let us prove for m in even integers, m plus n is even. So let's let m and n be even integers. Then m equals 2k1 and n equals 2k2 for integers k1 and k2. Now, let's notice that if I were to add m plus n, that's 2k1 plus 2k2, I would get 2 times k1 plus k2, which is 2 times sum k equaling k1 plus k2. Therefore, m plus n, or the sum of two even integers, is even. Let's do a second one. Let us prove for m in z, if m is even and n is odd, then the product m times n is even. So prove. Let m, which would be some 2k1, be an even integer, and n, which I'm going to write as 2k2 plus 1, be an odd integer. Then notice what happens when I take the product of m times n. This would be 2k1 times 2k2 plus 1, which would equal to 4 k1 k2 plus 2 k1, which would equal 2 times 2k1 k2 plus k1, which equals 2 times k, with k equaling 2k1 k2 plus k1, is even. Therefore, m times n is even. Let's do a few more. Let us prove for any odd integer n, 2n squared plus 5n plus 4 is odd. Okay, So let's look at the proof. Let n be an odd integer. Then n equals 2k plus 1 for some k in z. Now, let's consider this expression. 2n squared plus 5n plus 4, which I then could write as 2 times. Since n is odd, 2k plus 1 squared plus 5 times 2k plus 1 plus 4. And now if I run through the algebra on this, this is 2 times, what would this be? 4k squared plus 4k plus 1 plus 10k plus 5 plus 4. This would be 8k squared plus 8k plus 2 plus 10k plus 9. This would be 8k squared plus 18k plus, I'm going to write this 2 plus 9. While it is 11, I'm going to write it as 10 plus 1. And now if I notice right here in this expression, I can factor out a 2 from everything. This would give 4k squared plus 9k plus 5 plus 1. This would equal 2k plus 1. This is just some integer. Which is going to give us an odd integer. So the point is this expression, 2n squared plus 5n plus 4, is odd for any odd integer n. Okay, let's do another example. Prove that if m and n are perfect squares, then their product m times n is also a perfect square. So, proof. Let m and n be perfect squares. I get to assume the hypothesis, in this case, is true. Then m equals x squared and n equals y squared for some integers x and y. Now, let us consider the product m times n. M times n would be x squared times y squared, which I then can write as x times y quantity squared, using a property from elementary algebra, which I then can write as z squared for some integer z being the product of the integers x and y. So since m times n equals z squared, the product m times n is also a perfect square. Okay. Prove or disprove that 2 to the n plus 1 is prime for all natural numbers n. So my claim is that this is false. And this is a classic example. A lot of times when we do proofs, we might try to prove something directly. But if it doesn't hold true, then we need to come up with what's called a counterexample, just one example, to show that this statement is not true. So let us provide what we will call a counter example. So let us consider 2 to the n plus 1, and let's let n equal 3, which is itself a natural number. Okay? Then 2 this needs to be 2 to the n plus 1. That plus 1 does not need to be up in the exponent. Then 2 to the 3 plus 1 would be 8 plus 1, which is 9, is not prime. Therefore, 2 to the n plus 1 is not prime for all natural numbers n. It may be true for some n, but not for all n. Okay, now let us pivot and begin to take a look at what we would call indirect proofs, or proofs by contradiction. And so let's take a look at the quintessential proof by contradiction. Let us prove that square root 2 is irrational. So this is a very standard classical example of how we use the proof by contradiction. So let us first suppose the contrary. That is, square root 2 is, in fact, rational. We show this leads to a contradiction. If square root 2 is rational, then square root 2 can be written as a ratio a over b for integers a and b. Now, as a note, we will assume that this fraction or this ratio a over b is in simplified form. Meaning a and b are not both even. Since the square root of 2 equals a over b, if I square both sides, then I get 2 equals a over b squared, which implies that 2 equals a squared over b squared, which implies then that a squared equals 2b squared, which then implies that a squared is even. Why? Because it is 2 times b squared. But if a squared is even, then a is also even. So a equals some 2k for integer k. So recall that a squared equals 2b squared, and using a equaling 2k gives 2k squared equals 2b squared, which implies 4k squared equals 2b squared, which then would imply that b squared equals 2k squared. So b squared is also even. But if b squared is even, then b is also even. Thus, a and b are both even. However, this contradicts our assumption that a and b are not both even. Hence, our initial assumption that the square root of 2 can be written as a over b is rational is false. Therefore, we conclude that the square root of 2 is irrational. Let's do another proof by contradiction. Okay. So let us prove no integers x and y exist for which 24y plus let's change these x's and y's. We'll just say x and y. For which 24x plus 12y equals 1. So, proof, and we'll do this one by contradiction. So, let's suppose that x and y do exist, such that 24x plus 12y equals 1. Well, notice if I divide by 12, then I get 2x plus y equals 1/12. Now, this 2x plus y, this is an integer, this is an integer, so their sum must also be an integer. But notice that 1/12 is not an integer, which leads us to a contradiction. Therefore, no such integers exist. Such that 24x plus 12y equals 1. We're now going to segue into very specific proofs by contradiction, and we're going to begin to discuss what we're going to call proof by contrapositive. Now, if we recall from a previous unit, we said that P implies Q is logically equivalent to not Q implies not P. And so sometimes, instead of trying to prove directly if P then Q, it might be easier to prove not Q implies not P. So let's take a look at an example. So let us show that for all integers x, if x squared minus 6x minus 5 is even, then x is odd. So, proof. Using the contrapositive, we wish to show P implies Q by showing instead not Q implies not P. So for this statement, we have P implies Q. Well, what's P? Statement P is x squared minus 6x plus 5 is even. And what's Q? Q is x is odd. So my claim is instead of trying to do P implies Q, let's try to do not Q implies not P. So not Q then would be x is not odd, therefore x is even. And not P would be x squared minus 6x plus 5 is odd. So instead we wish to show not q, x is even, implies not p, x squared minus 6x plus 5, is odd. So let x be even. Then x equals 2k for some integer k. Well, if x is even, we now wish to show not p. So let's consider this expression, x squared minus 6x plus 5. I can write this as 2k squared minus 2 times, excuse me, not 2, 6. $2k plus 5. This would be 4k squared minus 12k plus, and I'm going to write this 5 right here as a 4 plus 1. And now I can factor out a 2 from this piece right here. So that's 2 times 2k squared minus 6k plus 2 plus 1, which is 2 times, this right here is simply some integer. So 2k plus 1, okay, which is odd. Therefore, we have shown not q implies not p, which is logically equivalent to p implies q. Therefore, our initial statement that we wanted to prove, that if x squared minus 6x plus 5 is even, then x is odd, is true using this proof by contrapositive. Let's take a look at one more example, and we'll do something called a proof of equivalence. So proof of equivalence looks like this. So P, if and only if Q, if we remember, this is logically equivalent to if P then Q, and if Q then P. So to do a proof of equivalence, I must show two things. I must show that P implies Q and that Q implies P. So let's take a look at an example. So prove for any integer n is odd if and only if n squared plus 1 is even. Okay, so what is it that I want to show? Okay, so this is This is n is odd if and only if n squared plus 1 is even. Okay, so let's go with the forward arrow first. And we get to assume that n is odd, and we must show that n squared plus 1 is even. Well, if n is odd, n equals 2k plus 1 for some integer k. And now let's consider n squared plus 1, which would be 2k plus 1 squared plus 1, which would equal 4k squared plus 4k plus 1 plus 1, which I could write as 4k squared plus 4k plus 2, which then I could write as 2 times 2k squared plus 2k plus 1. This is just some integer. And if I take 2 and multiply it times some integer, is even. So n squared plus 1 is even. So I just proved the forward arrow of this biconditional statement. We assumed that n is odd, and we showed that n squared plus 1 is even. Now we're halfway through. I have to go backwards as well. So now we get to assume that n squared plus 1 is even, and we must show that n then is odd. So we're going to do this one by contrapositive. Q implies P is equivalent to not P implies not Q. So assume not P. That is, n is not odd. So n is even. So n equals 2k for some integer k. Thus, n squared plus 1 would equal 2k squared plus 1, which is equal to 4k squared plus 1, which is 2 times 2k squared plus 1, which is odd. We just showed that not P implies not Q. So, by contrapositive, Q implies P is true.